Today we are starting chapter 20, and then this is part 1. We'll finish the part 2 on Monday. In this chapter, we are going to learn how to find the distributions of the difference of two proportions. We have dealt with one proportions already. Today we are going to talk about two proportions, find the distribution, confidence interval, and also conduct hypothesis testing, just like we did for the two proportions. With the one proportion we did earlier on, we know that the sample proportion, which is, so anytime we have p hat, we know this is the sample proportion. And then p is the population proportion. We know that the distribution for p hat is approximately normal. This is the mean and this is the standard deviation. So we've learned this already in previous chapters. And also in previous chapters, when we are learning about the properties of the expectations and the variance, we learned that the expectation of x minus y is the same as expectation of x minus expectation of y. And then the standard deviation of x minus y is the same as this SD squared is the same as what? So assuming x and y are independent, so as this SD squared is the same as the standard deviation of x squared. And we know that the standard deviation of x squared is the same as the variance of x. So the variance of x, or the standard deviation squared of x, plus that of y, and then the square root of that gives you the standard deviation of x minus y. Today we are interested in the difference of two proportions. Because we are dealing with two proportions, we are going to differentiate them. So we are going to have p hat 1 and then p hat 2. So p hat 1 will stand for the sample proportion for sample 1, and then p hat 2 will stand for the sample proportion of sample 2. Now this is the distribution. So the distribution of the difference of the two proportion, which is this one here, assuming all conditions are met, is approximately normal with the mean of this, and then this is the standard deviation. It is important for you to write out the formula, because some of your homework problems will just want you to click on the formula. So it is important to write that out. And then I also went ahead to also write out that the standard deviation of the difference of these two sample proportions is given by this. You can also see that the mean of p hat 1 minus p hat 2 is the same as p1 minus p2. It is here. This is the mean, this is the standard deviation. We've already learned in previous chapters that the mean of p hat is what? P. It is the same thing here. Remember x and y. So same thing. Mean of p hat 1 is p1. Mean of p hat 2 is p2. Sometimes we don't know the true values. What that means is that sometimes we do not know what P1 is and what P2 is. These are the true proportions of the two populations. So in those situations, if we don't know the true proportions, we cannot implement this formula because this formula requires us to know the true proportions, you see. So since we do not know that, we are going to use the sample proportions to estimate that. And when we use the sample proportion, it gives us what? The standard error. So when we do not know the true proportion, we are going to use the standard error to estimate the standard deviation. So when we do not know the true proportions, we are going to use the standard error to estimate the standard deviation. So this is the formula for the standard error. It is similar to the standard deviation. The only difference is that with the standard deviation, you have the true proportions, but with the standard error, it is the sample proportions. That is the difference. And then also to create the confidence interval, we are going to use this formula here. It is similar to what we did when we are dealing with the one proportion z stats, except that here, this is what true proportions, the difference of two proportions. So this is the difference. And then this value here, you shouldn't be scared about this value. This value here is the critical value. And then StatCrunch is going to help us compute that. This is the standard error, which we know from here. So you should also know that what p hat 1 is the same thing as what x1 divided by n1. So x1 is the number of what successes for sample 1, and then n1 is the sample size for sample 1. In that regard, we can also say that p hat 2 is the same thing as what number of successes for sample 2 divided by the sample size for sample 2. And then if you want to find a difference in proportion, you compute this and then you can find the difference in proportion. And so this is called you see here we have two proportions. So this is called the two proportion Z interval. It is similar to the one proportion, except that this is what? Two proportion. Like I did say, it is important that you have those formulas down and know that you can only use this formula when you are dealing with what? Two proportions, and then you don't know the true values for the proportions. And just like when we were dealing with the one proportion, we had some assumptions and some conditions. It is the same thing for the two proportions too. So similar assumptions like the one proportion we learned earlier on. The only difference is that here we also need the independent group assumption. So we know the first assumption here is that we want it to satisfy the independence assumption. So the individual responses within each group should be independent of each other. That is what the independence assumption stands for. And just like we know the randomization conditions, the sample size should be what? Simple random sampling. The sample sizes or the representative should be what? Random. And then the success and failure condition. You see, in the one proportion, we needed NP or NP hat should be greater than 10, and then NQ should be greater than 10, should be at least 10. It is the same thing here, except that here you have to do for both groups. So you have to ensure that NP1 and NQ1, both of them are at least 10. You do the same thing for group 2. So this is N1, and then N2, P2, and N2, Q2, both of them should be at least 10. So that is what the success or failure condition stands for. Like I have said, in the one proportion, we just do for one. But in the two proportion, you have to do for both groups. And then we need to also ensure that the responses in the two groups are also independent of each other. So these are the various assumptions you have to check for the proportion. Then you can proceed to use the Z distribution or the Z table. The other thing I want to talk about is how do we interpret the confidence interval for difference of the two proportions. It is similar to the one proportion, similar language, but there is a bit of tweak to that. And that is a tweak I'm going to explain. So anytime you conduct the confidence interval for the difference of the two proportions, one thing you have to look out for is you have to ask yourself, the values you got for the confidence interval, are they positive values? If they are positive values, then in your mind, it should tell you that what proportion 1 is greater than proportion 2. For example, if you also conduct and get 0.1, 0.4, these two values here are positive values. Is that okay? And so technically, it means that what proportion 1 is greater than proportion 2. Same interpretations like we did for the one sample, except that we'd have to add this to that. And then don't forget the interpretation is about the what? The true proportion. So you should be able to know that. And then if the interval contains only negative values, for example, like this, what it means is that what proportion 1 is less than proportion 2. So this is the trick to that. So I will encourage you to be able to know this. We would open StatCrunch and then do this examples there. But before that, let's try to talk about the hypothesis test. So to conduct the hypothesis test for the difference of two proportions, the null hypothesis is always this. So you see in the other one, we learned H naught, maybe P equals 0 or P less than 0. But here we are having what? Two proportions. So, and remember, I have told you that hypothesis is for the population. So you cannot put hat here. So it's always P and not P hat. So the null hypothesis is always this. The alternative depends on the problem. So the alternative could be not equal to, greater than, less than. It's going to depend on the problem. And then this is the Z test statistic value. So you can find P hat 1, P hat 2 minus 0, and then the standard error. We already know the standard error, which is this. So you can put that there, and then you can compute the Z test statistic for two proportions. And so let us see how to do this. Most of these things in chapter 20, StatCrunch is able to do that for you. But you should also know how to do that manually if you want to. So we are going to use StatCrunch to answer some of your homework problems. So let's open to chapter 20 homework problems. Let's open to question 1. So let's open to chapter 20 homework problems. Question 1. Let's learn how to solve for question 1. So it says that suppose an advocacy organization surveys 835 Canadians, and then 438 of them reported being born in another country. Similarly, 16 out of 131 US citizens reported being foreign born. We want to find the standard error of the difference in the two proportions. So you can see this, you can then go and use the formula if you want to, which is okay too. Otherwise, you could also use StatCrunch. Now, the question is, which of these two should be our P1 and which of them would be P1 and then the other would be P2? Most of the problem would give you a guidance. So for example, when you look at this one here, it says that let P1 be the sample proportion of citizens from Canada who reported being born in another country, and then P2 is for the US citizens who are foreign born. So when we look at this one here, we know P1 is for the Canadians and then P2 is for the US citizens. So then it means that let's try to get our data. So since P1 is for the Canadians, we come back to our problem. And then when we read, it says that the advocacy organization surveys 835 Canadians. So it means that N1 is 835. So you have to write that N1 is 835. And then out of that, 438 of them reported being born in another country. So N1 is 4,835. It means that X1, which is the number of successes or the number of foreign born, is what? 438. I chose N1 and then X1 to be Canadians because the question guided me to do so. Is that okay? Now let's get to N2 and P2. So P2 is for the proportion for the US. And so we can see from here, N2 is 131. And then X2 is 16. Can you all see that? Good. So once you have this information, we can now go and compute the standard error of the difference in the two proportions. You can do this manually. You can compute P hat 1 to be X1 divided by N1, P hat 2 to be X2 divided by N2, and then you can implement the formula we talked about in the slides. Or you could use StatCrunch. And so to use StatCrunch, open StatCrunch. Let's go to Stats. We are dealing with proportions. So proportion, but this time around, we are dealing with what? Two samples. And then we go to with summary. So we go to Stats, proportion stats, two samples, and then we go to with summary. Do you have that opened? Okay. Now let's input them. Be very careful how you input them. You see sample 1. Here are sample 1 is the Canadians. So we need to enter that first. So let's do that. 835. No, X1 is not 835. X1 is 438. And then here is 835. And then X2 is 16. And 2 is 131. So we just want the standard error. So if you want the standard error, let's click on the confidence interval. You can put any value here because this value just computes the Z, so it doesn't matter. And then let's click compute. Now I recommend you to use this because in the earlier class, we used this to get a standard error. It works for some problem and some way, somehow, it didn't compute the other problems correctly. So let's try to use the confidence interval section to get the standard error for the difference in the two proportions. We hit compute, and then you can see this is a standard error. Is that okay? So let's try to report that. 0.03342. Okay, that worked. Now let's get to question 3 now. So we are done with question 1. Let's go to question 3 now. So same approach, try to read the problem and then understand. So here it says that an advocacy group organization surveys 946 Canadians, and then 183 of them reported being born in another country. And then for the US, 190 out of 1226 reported being foreign born. And so here we have an idea. Researchers want to test if the proportions of foreign born are the same in the US as in Canada. So you see, with this problem, we have been given an idea about how the hypothesis should look like. Is that okay? And so when we read this problem here, we've been told that we should assume P1 to be the proportion of foreign-born residents from Canada. So P1 is still for Canadians, and P2 is for the US people. So to do that, we need to be able to do N1 for Canadians, and then we would assign N2 for the US citizens. So we can see from here that what is N1? In my example, what is N1? 946. And then X1 is 183. N2 is 1226. X2 is 190. The first question says that we should find the difference in the sample proportions. So you can compute P1 and then P2 and find the difference. StatCrunch also does that for us. So we can do that in StatCrunch too. So data proportion stats to sample with summary. And then let's choose the confidence interval here first. And then we can hit compute. When we hit compute, you see we are interested in the difference of the two proportions. So you see that gives you the value here, the sample difference. This is the difference of the two proportions. So that is what we need to report. That is 0.0384. So the next thing is that we want to write the appropriate hypothesis. So to be able to do that, now let's get to the problem and see if we can formulate the hypothesis. The researchers want to test if the proportions of foreign-born are the same in the US as in Canada. And so, what do you think the alternative would be? The alternative would be that they are not the same. Is that okay? So they are not the same. That is what not equal to. Is that okay? Even if you get confused and then you want to even guess, you should be able to see that A is out of the equation because the null hypothesis here is what not equal to. Is that okay? And then D is also out of the equation because the null hypothesis here is what greater than. We don't want to have those signs in the null hypothesis. Good. So it means that you have been able to improve your chances of guessing, but I don't recommend you to guess, but I just needed you to be able to rule out certain things when you have like multiple choice. So here we agree that what the null hypothesis is what equal to an alternative is not equal to because the researchers wants to test if they are the same. The alternative is that what they are not the same. Is that okay? So that is C. Bless you. Now we want to compute the test statistic. So to do that, we go back to our StatCrunch. Let's get to edit, and then let's move the confidence interval to the hypothesis part. Is that okay? And then make sure that we have inputted the hypothesis rightly as the problem is saying. So in my situation, it is correct. Is that okay? And then all you have to do is to hit compute. So when you hit compute, you have this. We are interested in the test statistic. This is the test statistic. So the test statistic is what? The Z stat.
Why is there minus zero in the Z stat equation? Like, I was getting wrong.
The formula.
Yeah, it has it's like P hat or P1 minus P2
minus 0. Because the null hypothesis is P1 minus P2 equals 0.
Okay, I guess, yeah, you move the 0 onto the other side. Okay, I guess that.
Yeah. Remember when we are dealing with the one proportion Z stats, when we are computing the Z stat, we take the p-value on the null hypothesis. Here it's 0, so that is why it's 0. Anyway, good question. So the Z stat here is 2.5 357. The Z-stat is not a standard error. Is that okay? There is a critical value which we say critical Z. The test statistic in StatCrunch names that the test statistic is always called Z-stat in StatCrunch. So you should always know that. So that is what 2.3571. So they want it 2 decimal places. 2.36. The next one says that we should find the p-value. If you input your hypothesis correctly, you should have the p-value. The p-value I have here is 0.0184. You can see the p-value is here. 0.018 because they want me to round it to what? 3 decimal places. Then now we have to state the conclusion. And then you can see from here, you were given an alpha level of what? 0.05. I've already talked about this. I've repeated it many times. If you are given an alpha level, you decide based on that alpha level you have been given. If you have not been given, like in the previous chapters we did, we assume alpha to be 0.05. Some of you would have alpha to be 0.1, so you have to decide based on that. Is that okay? And so to make that decision, now tell me, is the p-value here compared to alpha, is it smaller or larger? I have a p-value of 0.018. Is it smaller or larger compared to 0.05? It's smaller, right? And if the p-value is smaller, what do we do? Do we reject or fail to reject? If the p-value is smaller, we reject. And anytime we reject, there is what? Sufficient evidence. Is that okay? If we fail to reject, there is what? Insufficient. There is no evidence and all those sort of stuffs. Good. Now let's get to question 7. Let's get to question 7. There we go. So here we are told that in 1996, researchers investigated the effect of weed-killing herbicides on house pets. So they examined 819 cats from homes where herbicides were used regularly. And then they diagnosed lymphoma in 414 of them. And then of 127 cats from homes where no herbicides were used, only 18 of them have lymphoma. So we can see that what they are trying to do here is that they have some homes where they used herbicides and then they diagnose those cats there. And there's some homes that do not have herbicides and they also diagnose lymphoma. So the first one is given us. So A says that P1 should be the sample proportion of cats with lymphoma from homes where herbicides were used regularly. So based on this, we can see that N1 is 819 because P1 is for homes where herbicides were used regularly. And then you can see 819 of the cats from where herbicides were used regularly. And then X1 is 414. We can see N2 is 127, and then X2 is 18. Now we want to compute the standard error. So to do that, we go to Start Crunch, Starts, Proportion Starts to Sample with Summary. And then let's input our data. 819, 414, 127, and then 18. So if we want the standard error, let's try to put the cursor on the confidence interval side and then try to compute that. Oh, I think I inputted this wrongly. Here should be 18, and then here should be 127. I think I did the same thing here. 414, and then 819. So always you have to check that, because the number of successes cannot exceed the number of observations. So you can see in my situation, I made a mistake and then I inputted them wrongly here. So don't make that mistake. And then what do we want? We want the standard error. This is a standard error, which is 0.0355539. So let's try to input that to 4 decimal places. And then the second one says that create a 95% confidence interval. So to do that, I'll just go to options, edit. Make sure that here is what? 95. Is that okay? Make sure that here is 95. Yours could be 99, but mine here is 95. So make sure that this is correct. And then the lower is what? 0.2941. The upper is 0.4334. So let's try to input them to 3 decimal places. 0.294, and then 0.433. The last part says that we should choose the appropriate conclusions below. We know that confidence interval just gives us the idea that the true proportion or the true difference should be within this interval. And so the samples here, mine here was about cats, yours could be dogs. So now it's about what? Cats, not sample cats. So you can see from here, A is out because it says that the rate in samples cats, which is incorrect. So A is out. Is that okay? Look at this sentence here, takes A out. Samples of cats, no. Now, 95% rate of pets, it's not pets. We used cats in this example here. Mine was about cats, so that means that B is out. So the answer is C. You can see that there is 95% confidence that the lymphoma rates of cats in homes where herbicides was used is greater. You see, you can see the confidence interval here is positive. And then P1 was where represents the homes where the herbicides were used. So we click on that. And then let's get to the last one, 8. So to do 8, it's important that we read the problem. So a journal reported a study examining the possible impact of air pollution on the weight of babies. Researchers found that 8% of 171 babies born to mothers who were exposed to heavy doses of air pollution in the city were classified as having low birth weight. So these were people who were exposed to heavy pollution. And then only 4% of 2,400 babies born in another hospital in a city whose mothers have not been exposed to air pollution were similarly classified. Now, the question says that does this indicate a possibility that air pollution might be linked to a significantly higher proportion of low weight babies? So now they give you here P1, let P1 be the proportion of low weight babies born to mothers who were exposed to air pollution. So those who were exposed to air pollution. So it means that N1 is what? 171. X1 is what? 0.08 times 171. N2 is what? 2,400. And then X2 is what? 0.04 times 200. Now, we want to write out the hypothesis. So to write out the hypothesis, we can clearly see that A is out because the null hypothesis have less than here, which is incorrect. Now, because here is what? Significantly higher, it means that our hypothesis should be C, which is what? Greater than. Is that okay? So we check on that. And then now we want to compute the test statistic. So let's try to compute the test statistic using StatCrunch. So let me start all over again. So stats, proportion stats, 2 samples with summary. So here, N1 is 171. And then here is 0.08 times 171. N2 is 2,400. And then X2 is 0.04 times 2,400. And then the hypothesis is here should be what? Greater than. So you have to make sure you input the hypothesis correctly. So here is greater than. And then let's hit compute. What were we looking for? We're looking for the test statistic. This is Z stats. So that is 2.50073. We want to 2 decimal places. So 2.50. So we want to put in the p-value. The p-value is 0.0062. P-value 0.0062. So we want it to 3 decimal places. So in my case, it's 0.006. Okay. Now we want to state the conclusion. So to state the conclusion, we are comparing this p-value to an alpha level of what? 0.1. Is the p-value smaller or greater? Is it small or large? Compare this 0.06 to an alpha level of what? 0.1. It's small. If it's small, what do? We reject the null hypothesis. Is that okay? And then when we reject the null hypothesis, there is what? Sufficient evidence. So we conclude that here it's the what? The is greater than, so the population proportion of low baby born to mothers who are exposed is greater than that. We check that. And then the last one says that we should fill out the confidence interval. So how do we fill out the confidence interval? So here it is one sample test, right? The alpha is what? 0.1. So it means that we need to conduct the 1 minus 2 alpha confidence interval. So that is going to be what? The 80%. So I come here, confidence interval. You have to change this to 80. Because this is what? 1 tilde. So I multiply the alpha by 2. I subtracted 1, and then I multiply everything by 100%, which gives you 80%. And then I hit compute. I have this. The lower is what? 0.01292. The upper is 0.06. Lower is 0.0129. Upper is 0.0670. 3 decimal places. 1, 3, 0.067. So you see, it has worked. And then we have to finally put in the interpretations. So we can see that we are talking about the true population proportion. So one can be 80% confidence that the population proportion, not the sample proportion. So this is 80 is between, so we put those values here, and then higher for mothers exposed to levels than those who were not exposed to. So you multiply this by 100. Let me try to see. 1.3, I guess. And then 6.7. Yep. So that is how to answer that. And then you should be able to do the rest. We will do part 2 on Monday and then start the test review on Wednesday. So I'll see you next week.